start. Okay. Number 6. A compound decomposes at 27 degrees Celsius in a first order process that has a half-life of 693.1 seconds. So I'll write that down. Has a half-life of 693.1. Period. A. What is the rate constant for the decomposition? The rate constant for the decomposition at 27 degrees. I had to include that. That wasn't spurious information. At 27 degrees. The rate constant, because the rate constant depends on what? Temperature. It's a constant at constant temperature. So now, at this point, this is pretty straightforward. We have that how do I express this? Okay. I'm having to do the integrated rate law in my head right now. Okay. The concentration, so I don't have anything to write, but the concentration would be time T1/2 is going to be equal to A, we'll just say that time T at T 1/2 is equal to natural log 2 over K. Okay? And so, no, T1/2. I don't know what I'm doing. I didn't need that. T1/2, the half-time, the half-life. I didn't need that concentration. The half-life is equal to the natural log of 2 divided by the rate constant. This was, we found this when we did the integrated rate law, and we talked about that some time ago. And the natural log of 2 is, and the half-life is equal to 693.1 seconds. Okay. And the natural log of 2 is equal to 0.6931. How do I know that? I can memorize that fact, or I could just simply take that the natural log of 2 is equal to 2.303 times the log of 2, which is 0.301, which equals 0.6931. So in case you forget what the log of 2 is, or what the natural log of 2 is, you already know the log of 2. Just multiply it times 2.303. And that gives you the natural log of 2. Okay? So that part's the easy part. And now I want to know the rate constant K is going to be equal to to natural log of 2 divided by t 1/2, which is equal to 0.6931 divided by, or let's rewrite that, 6.931 times 10 to the minus 1 divided by 6.931 times 10 to the minus 2, and that would be, include the unit seconds. Okay? And so the math is very difficult. 6.931 divided by 6.931 is 1. 10 to the minus 1 divided by 10 to the minus 2 is 10 to the 1. So it's 10.
So it's 10.
Oh,
10 per second. That's the rate constant. First order processes have units of per second. Okay? Well, did I have a similar problem on the other one?
Yeah, it's different answers.
Yeah, it was probably a little different. Let me look at the question. First order process, 600.
Did you copy the half-life time? Is it to the negative 2? Or is it just to the 2?
693.1, did I have 693.1? 1, 2.
No problem.
it should have been to the point 1, because instead of the top,
Oh, it's,
the numerator is wrong.
it's not, oh, 2.
There.
There's where I made my mistake. Thank you. So I screwed up, didn't I? Okay. 10 to the minus 1 is 10 to the minus 1 divided by 10 to the 2. It's different, isn't it? That's what? 10 to the
Minus 3.
10 to the minus 1, okay, 10 to the minus 3 per second. Much better. Thank you for catching that. Between giving you the wrong keys and screwing up like this, so it's the
That
same.
means we're awake.
That means you're awake. Thank you. Yeah, I'm glad you're. Yeah. Somebody here is, not me. Okay, are we done with that problem? Oh no, it's that part A. Part B. Where's part B? Okay. How long does it take for the concentration of the compound to be reduced to 1/8 of its original concentration? So the answer here was 10 to the minus 3 per second. And part B. How long does it take for the concentration to be reduced to 1/8 its original value at 27 degrees? I have to put that in at 27 degrees Celsius because this is all temperature dependent. What do I do? What happens to this as a first order process? What happens to it with every half-life? So, yeah, I want to write mathematically. I'm going to go, the half-life is the time it takes to be cut in half. Okay,
So,
that's
just
by
by-
definition, so,
About the total amounts, right?
so 1/8 is equal to, the concentration of A naught, divided by, okay. Yeah, H is equal to 1/2, that's what I wanted, to the n. That's what I wanted. 1/8 is 1/2 to, because it's reduced 1/2 in each half-life, so how many half-lives?
3.
Yeah. And therefore, n equals 3, and then what was our, so t is equal to 693.1 times 3 equals, now I gotta go over my scratch paper, 693.1, 3, 3, 9, 7, 6 times 3, 18 is 20. That would be seconds. Yeah. Okay? So that one looks more formidable than it is. It's actually very straightforward. By definition, the half-life is the time it takes to reduce the concentration 1/2 its original value. Okay? This is actually going to come up very, it's going to prove to be very handy and useful when we start discussing nuclear, which is coming right up. We start talking about radioactive decay, which is a first-order process, and the half-life is one of the key features. Okay, that wraps that problem.